Hello everyone, welcome to our presentation. Today we are going to present you of our final presentation. I am Çise Lal Demirel from Industrial Engineering Department.
Hi, my name is Arda from Computer Engineering. For our final presentation, first we are going to introduce you our dataset and our aim, then the problem and our motivation to solve this problem. After that, we will talk about data manipulation and target manipulation respectively. Then we will talk about how we applied smooth to our data and features that we add. Lastly, we are going to talk about our hyperparameter selection and model selection. Next, please. Our dataset is synthetic dataset. We found this dataset from Kaggle. It is predictive maintenance dataset by Stephen Muscat. Our aim is to predict the machine fails or not, and if it fails, what kind of fail it is. We use supervised learning and multi-class classification. Next slide, please. Our problem and motivation, instead of routine maintenance, we can try to predict if the machine needs maintenance or not. Knowing if a machine needs maintenance before it breaks down, save us time and money. It is cheaper to fix the error before the machine breaks down than to replace the whole machine. Next slide, please. In the beginning, we had 10K samples and 13 features. We have no missing data. But as you can see in figure on the right, our data set was imbalance. So we need to fix this. We will talk about details and manipulations in the next slides. Next slide, please. These are our initial features. We added some new features after USC. We have UID and product ID. We have type, low, medium, and high. We have two temperatures informations, air temperature and process temperature. Also, we have rotational speed and torque of machine and tool-wear feature. Also, we have machine failure labels and it shows machine is fail or not. Next slide, please. These are our failure types. If machine fails, we are not gonna say machine is fail. Instead of this, we are gonna say it's with these failure types. These are tool-wear failure, heat dissipation failure, power failure, overstrain failure, and random failures. Next slide, please.
Hi, I'm Eray Bedir from Information Systems Engineering. We had some problematic data, and we thought that we should just delete it at the first. But our supervisor, Professor Murat Karakaya, said you have an imbalance in dataset. You shouldn't delete minority classes. So we split the 24 samples with more than one failure type to different samples with different failure types, and UID column was removed. Next slide, please. In 18 samples, where machine failure was 0, but random failure was 1, we made the machine failure 1 instead of removing the data. Next slide, please. We have added a new column to datasets called failure type and moved all failure types and failure situations to it. At the right bottom corner, you can see it. 0 represents no failure and the other 5 represents different failure types. Next slide, please. Our justification for these manipulations, because it was easy to interpret the data, and we can use a single model to train the data. Next slide, please. This is the data set after fixing these problematic samples. No data was removed. Individual failure features and machine failure was removed and replaced with a single column. Failure types and quality were included. Next slide, please. You can better see the imbalance we had at the first here. Next slide, please.
In order to fix the imbalance in the data, we use mode which works by selecting examples that are close to each other and draw a line between them and add a new sample to this line. As you can see in the figure at the right side of the page. Our smooth application we took the highest instance as a reference and equalized the number of minority classes. So we selected only 20% of no failures to oversample, and our demanded number of 1K. A distribution of targets after we apply smooth is like that. We balance the minority class and major class, minority classes and major class, as you can see here. After smooth, we split data by 80 to 20% before training and testing the data. We have tried some models without hyperparameter configuration, and we, as a result of the model results, we choose random forest as our baseline model. Here, the model performs well in test results with 0.99 approximately on F1 score. But for the HDF failure, which is our fourth failure, the F1 score is 0.48, and this is pretty low results. And in the confusion matrix, you can see the in the first column, it shows the prediction of the targets, and it's almost fault. It creates fault, and we need to fix it.
Hello, I'm Zeynep Atav from software engineering, and in our previous presentations, we had thought that oversampling was causing some kind of error, but after checking our results better for the specific targets, such as we checked the majority class as 0 as no failure, and we took the sample of the fourth failure HDF, and we saw that even if the model performs worse than before in the test results with the 0.971 F1 score, in the confusion matrix, we can see that there are the correct results, and we fix these by showing the percentages of the actual value instead. Next slide, please. And as you can see over here, we have all of the results like side by side to be able to compare. Before our oversampling for our fourth target, our F1 score was really low at 0.4, but after we oversampled, we saw a significant increase in the F1 score, and as well as the rest of the parameters. And you can see that from the confusion matrix that before oversampling, since the number of samples for each failure type was really low, such as let me annotate over here, 15 for the first failure type, 78, 76. It was unable to predict it correctly, and it predicted that even if there was a failure, such as the first failure, it predicted as there was no failure. But after we oversampled, since we were able to increase the number of the minority samples, it was able to make better predictions. Next slide, please.
May I ask a question, Zeynep?
Yes, sure, Hocam.
Here in that slide, on the left side, before oversampling result, precision looks like 0.75 precision.
Yes, Hocam.
Recall looks like 0.35, 35%. Right?
Yes,
so here, what is the precision means here as a metric?
Like precision means like whether it's going to be predicting the correct version, as far as I understand of it. Like it's probably the ratio of, let's see, this is for the fourth one, right?
Yes, but what's the precision means
This one,
here?
like it
What's
has
the difference between precision and recall here as a metric?
What I'm thinking is that precision is like it's according to the ratio of what it predicts instead of the actual value. Like, for example, it predicted 45.7 of all of the samples correctly, but it predicted that like 47 of them as no failure and various ones as wrong failure types. That is the precision, I believe, the ratio between those. And recall, I think, depends on the test.
Nope. Okay, Çise?
Hocam, I don't know the difference between them.
All right. Seyit Cem?
Precision, true positives over all positives, I think, class. Right?
Then recall?
I don't know, sorry.
Okay. Arda?
So I think recall is something like if we need to predict as positive, and if we predict positive, recall high. If it's positive and we predict it as negative, recall will be low.
Are you sure?
Or something like that.
Are you sure? Eray?
No, but it's something like that.
Eray.
I can't really add anything over.
Okay, actually, recall means that for the target value 4, actually, if there are 100 of target values in your test data, you only correctly identify 35 of them. Recall is that. But if the precision is 75%, assume that there are 100 prediction of you made as 4, only 75 of them actually is 4. So you need to understand these metrics, and I gave you as a homework, right, to read and understand the classification metrics and the regression metrics as homework, right? So in the exam, I will ask this. In your project, you need to understand and explain this to me, because if you check that, the precision looks like good for the class 4, but recall is low, right? And on the other side, after oversampling, precision and recall, both of them good, right? Actually, I could have deeper questions here. Why would like that? But you need to understand the precision and recall carefully, right? And my last question again, let's begin with Zeynep. Zeynep, if you notice that here is F1 is 0.48, right?
Yes,
Zeynep, so what is F1 score?
Actually, what I thought was, as Arda said, for the recall, that it's the number of true positives over the, like, I couldn't explain it, but like, it's basically how correctly it classifies it.
Not really.
Okay.
Not really. Çise?
Hocam, I think number of true positives over all positives. I know it as.
Okay, not really. Seyit?
Hocam, same, I think.
Okay, I will not enforce you much, but actually F1 is the harmonic average of precision and recall, right? Harmonic average of precision and recall with respect to first harmonic. Okay, so if one comes there are F2 scores, F3 scores, whatever. But basic definition is like that. So I strongly suggest you and every team member and all other teams, you need to understand the metrics clearly with respect to classification and regression problems. So sure, there will be questions in exam, in both exams. Okay. So they heard that this study and understand. Otherwise, you cannot compare your models and hyperparameter values without understanding this. Okay. Let's continue.
Okay, hocam. And as we talked about in our previous slides as well, about our previous presentation, we decided that we needed to construct new features as per your recommendations because we had a less number of features. And we had searched up the definitions of our failure types, and according to that, after having seen the correlation, let's say between the rotational speed and torque, we decided to put this as the power metric to maybe, so that maybe it will have some benefit in terms of the power failure. And there's also the heat dissipation, which means that the transfer of heat between objects. And since we have a heat dissipation failure and our air temperature and process temperature features are seen as really strongly correlated, we decided to take the difference of these in order to be able to predict our heat dissipation failure more correctly. And we also added another one called strain, which is the deformation of the moving tool parts in terms of the tool wear and torque, because as the machine moves like with more force, it's going to get deformed more. Next slide, please. And before our base,
Zeynep,
our base model.
in the original dataset, how many features were there? After you add these new features, how many total in the modified dataset?
Hocam, this is a bit interesting question because in the beginning we had 13 features, we removed some of them, and now we added some of them. So in the end, we ended up with 6 failure types and 4. So we should actually end up with 13 features again, I believe.
Yes,
currently,
but before presenting these results, it's a good habit to share what was the dataset, now what is the dataset, or what
actually
becomes,
we mentioned
right?
how it was before, but yes, you're right. We didn't mention how many features it became, but we added 3 new features. Okay, so after the addition of these new features, we observed that the performance of our base model, which was random forest, improved. So as you can see, and before the feature construction, our F1 score, which we observed the most actually, was 0.971, and it became 0.983.
Zeynep, may I interrupt at this position?
Yes, hocam.
Okay. Could you please explain me here what's happening here in that confusion matrix, on that arrow, on that line, on that row? Could you please explain?
Hocam, let me also get my annotation. Okay, so over here, we have the actual number of the second failure type, which is, I believe, overstrain failure. So it predicts 95% of them correctly. When the actual was 2, it also predicted 2, like this. And for the second failure type, it also has the highest confusion rate, let me say, between the second and third failure type. So it mistakenly, even if the actual failure is 2, it predicts 2.4 of the samples, 4% of the samples as the third failure type, and 1.2 as 4, and 0.8 as 5. And yes, very negligible amount as no failure occurring.
Yeah. So I would like to ask Çise.
Yes.
What do you think about the 4th row here? How can you explain us 4th row? What it means?
Hocam, first of all, the model, the actual fault was, actual failure was 4, and our model truly predicted as 98.2 percentage, and it predicted false as the no failure with 0.5 percentage, and predicted false as 1 percentage the second failure, and the third failure also.
Do you think it is like that or something different?
Yeah, actual was 4 and predicted was, for example,
Yes, correct. Now we talk about the precision and recall by looking these row and the percentages here. Can you predict the precision or recall from that information?
yes,
Do you
actually.
understand my question?
Yeah, hocam anladım.
I am
Yes.
asking that just looking the fourth row here. Can you tell me about the precision or recall for the fourth case? Precision or recall?
Hocam,
Which one?
will I answer?
Yes, please.
Me? Okay.
Yes, please.
We can calculate precision by looking at the fourth row.
Precision or recall?
Hocam, precision, I think.
I think it is recall.
Hocam, I feel like it's recall because when you look
Why?
at the correct ones, this one's 98.2. This could have been rounded off.
Why it is recall? Because as I try to explain, recall means that how many four cases exist in your data set and how many out of them correctly located in the model, right? That's the if I show you here, that's the diagonal part actually gives you the recall for each class. Am I right?
Yes, hocam.
Do you agree, Zeynep?
I agree, hocam.
Çise?
Yes, hocam, I understand.
So that's the recall because recall gives us that on that arrow we have this number of samples belonging to class 4, but only out of this number we decided predicted correctly this number. So actually this is the definition of recall. But for the precision, how can you find the precision? By using the confusion matrix. Anybody knows? Orhun, Eray, Seyit. I just provide you simple explanation for recall. How can you find the precision by using the confusion matrix? Nobody knows? Okay.
You should check true positives and false positives.
Here we have the confusion matrix. Everything is on here.
Yeah.
True positive, false positive, everything is here. Can you find 0.98.5 by using this table?
I think you can find, but I can't see how.
All right.
Right now.
Please learn. Okay, I will not go to details,
Okay.
but try to understand this confusion matrix with respect to precision and recall. And of course, classification accuracy. But here, please pay attention. You are using, okay, it's a good idea to use the minor class, right? Minority class. Okay. Okay, let's continue.
Okay, John, then next slide, please. Okay. And so the next thing we did was, after having decided our features had a positive impact on our base model, we actually have to choose our actual model. So before doing that, we need to test different models and tune their hyperparameters. So we first split the data set, the whole data set, in a 80-20 ratio for training and testing respectively. And the 80% portion above was split again into a 90-10% ratio for training and validation this time, as per what our instructor said in our previous presentation, because the number of samples already decreased after we had an 80% split. Next slide, please. And we tested various models such as KNN, the normal tree, and random forest, and we tested 3 parameters for each. And KNN5 was chosen according to between the KNN1, 3, and 5 by taking the area under curve into account, since it's a more significant model performance metric. And we saw that there was no difference between the tree 100 and tree 1000. So we selected the 100 trees for the performance reasons, because it takes very long for Orange to compute the result of 1000 trees. And similarly, there was no difference between the random forest 50 and 20, and we chose the 20 again for the performance reasons. Next slide, please. And over here, since it's harder to see the parameters, we decided to make this into a bar chart to visualize them better. And as you can see over here, the KNN5 and 3 are really low in comparison to the rest of them. And also KNN1 seems to overfit if you compare the train and test results of KNN1. Allow me to clear. And
I would like to thank you for the team presenting in all the results in two figures, right? Last time I requested this and you have done this. Now it's easier for audience to follow with you, right? Because in the last time you have just screenshots and it's not easy to follow what we have found in the end of this a number of experiments, right? Now it's a good idea to present these visual figures, bar charts, right? To convince the audience that some model, some hyperparameter is better than with respect to some metrics to other. So it's a good habit to present like this. Okay.
Thank you, Hocam. Well, actually, it's a bit still hard to see the very small differences, but we can see that between the trees, there is like very minor difference. Allow me to mark it down. For tree 100 and tree 10, the graphs are exactly the same, as well as over here. And we can see that between the train and test data of the trees, that the precision metrics increased, and really similar results for random forest. It classified really almost perfectly in the training session, but afterwards there was only a very minor decrease, and that the random forest 20 actually performs better. Next slide, please.
Hi, I'm Seyit Cem Yılmaz from Computer Engineering. This is our ROC curve for hyperparameter tuning models that we used for, again, heat dissipation failure. When some models has good curves close to 1.0, some models didn't enough the performance. Next, please. We split our data set into 80% to 20%. 80% is for training and 20% for testing. The train data set was used in training the models with tuned hyperparameters, and testing portion was used in testing. This 20% portion has never seen before by the models in hyperparameter tuning. Next, please. In model selection results, performances of the models were compared according to an AUC, F1, and ROC curve results. We decided to choose a random forest 20 model. KNN5 has the lowest accuracy among all three models. 100 has good results, but we decide to choose random forest 20. Next, please.
But Seyit, may I interrupt?
Yes hocam.
Actually, in the previous slide and so far, you are always reporting according to class 4. Am I right?
Yes hocam.
But
This
you
is
have
true.
already checked the others. Am I right? The average.
Yeah, we checked it.
Yes, we checked, but we want to put there
Well, I
minority
understand, but
class.
your model selection does not depend solely only the class 4 results.
Yes hocam, I know that. Yes, you're right. But we only put fourth phase
Yes,
life
but
here.
if I were you, I would create another diagram, right? In that diagram, I would present all 4 or 5. Am I right? 5 classes, right? You have actually.
One no failure and 5
no
failure type.
right? So I would
Yes.
put all of the failure types, for example, F1 score on one slide.
Yes hocam, you are right, but we put for other slides only for 4.
I understand, but in the model
Yes.
selection, for the model
Yes,
selection, if
we
I were
consider it,
you,
hocam.
I would put a augmented slide, augmented figure, so that we can see that for each of the classes, what the models perform, how the model performs for each minority classes.
Okay hocam.
So it would be much more beneficial for us when try to select, because maybe this model works with class 4, good, but maybe it fails for class 5, which is another minority class. Do you understand
hocam,
my
you're right.
point?
Yes, I understand.
So, Çise, in your final report, please update this part.
Okay, Cem, we will put it. Okay.
Okay, thank you.
Next, please. The previous results can seen here as a bar chart again. Next, please. Confusion matrix of the random forest 20 can be seen there for train and test. On the diagonals of the table shows correct predictions. Next, please. Again, we have here an ROC curve. Our random forest 20 model can be seen close to 1.0 nearly. Next, please. And this is the results of our study in orange. Next, please. Thank you for your listening. Any questions? If that.
Okay, thank you for the presentation. But as during the presentation, as I already pointed out with my questions, you have to be acknowledged about your metrics carefully and deeply and use accordingly. And in your presentation for the model selection especially, please share or augment all the results for the minority classes and present like that. Okay, that's my comment.
Okay, hocam.
Okay, hocam.
Thank you for the presentation. We will continue with the next presentation.